Alright, so now we'll go over the stereochemistry problems. So in this first set of problems, we are just trying to determine R and S for the stereocenters listed. In our first molecule, valine, we have a single stereocenter located right here. The highest priority group is the nitrogen. Then we have 2 carbons and the low priority group, which is not drawn in, but is a hydrogen pointing back. Between the 2 carbons that are drawn in, we have on the left a carbon that's bonded to 2 other carbons, and on the right a carbon that's bonded to 2 oxygens. Carbon bonded to oxygens is higher priority than the carbon bonded to other carbons. Our lowest priority group, the hydrogen, is pointed back. We don't need to rotate the molecule. Our arrow goes counterclockwise, and so our stereocenter here is S. Naproxen also has a single stereocenter located here. The low priority group here, the hydrogen, is actually pointed forward. On the left side, we have a carbon that has bonds to 3 oxygens. On the right, this carbon has 3 bonds to carbon, and the methyl is 3 bonds to hydrogen. So oxygen, higher priority than carbon, higher priority than hydrogen. Arrow goes clockwise. But because our high priority group, the hydrogen, is pointing forward, we have to take the opposite, and so this stereocenter is S. In part C, we also have 1 stereocenter that's indicated. I would note there's a second stereocenter over here, but we're not going to worry about that because I didn't indicate directions for the substituents there. But bromine is the highest priority. And then we have 3 carbon groups. The methyl is the lowest priority of those 3 groups because it's a carbon bonded only to other hydrogens. On the left, we have a carbon bonded to 2 carbons. That's higher priority than on the right where we have a carbon bonded to 1 carbon. So the left, even though it's a much smaller substituent, we have a difference just 1 carbon away, and so that matters. That huge rest of the molecule doesn't come into play. Our low priority group, the methyl, is already pointing back, and so we don't need to adjust anything. Our arrow goes counterclockwise. We have S. Part D, we have 2 stereocenters, and we'll start by filling in the hydrogens, which at both centers are a low priority group and are pointed back. So we start with our carbon here. The other 3 groups are all carbons, so we have to look at what those carbons are attached to. On the left, this carbon that I highlighted in green is attached to carbon, hydrogen, hydrogen. Up above, being that carbon, that's attached to carbon, carbon, hydrogen. And to the right, that carbon is attached to bromine, carbon, hydrogen. So that bromine is the highest priority. So it's 1, 2, and 3. Arrow goes counterclockwise. And that makes this chiral center S. Now I'm going to erase a lot of that so we can see the other chiral center. But at our other chiral center, the bromine is higher priority than the 2 carbon groups. Again, our hydrogen is 4th. To the left, we have a carbon bonded to 2 carbons. That's higher priority than carbon bonded to 1 carbon. Counterclockwise, also S. For threonine here, first chiral center, oxygen, carbon, carbon is R. And then we have 1, 2, 3 this way, gives us S. And then for glucose, again, just doing the same steps again. We start here on the right side. Oxygen is highest priority. To the right, we have a carbon bonded to twice to oxygen versus just once. So 2, 3 makes that one R. Our next chiral center, oxygen highest priority. On the left, we have a carbon that's bonded to a carbon and an alcohol. Same on the right. But on the right, if we go one carbon further, we have the carbonyl, which wins out over the alcohol. So 1, 2, and 3 there. Gives us S. Moving over to the next alcohol, top priority is the OH. Second is to the right. Third to the left, we have R. And our last center, oxygen is highest priority. To the left, we have a carbon bonded to an alcohol. On the right, we have a carbon bonded to an alcohol and another carbon. That'll make that higher priority. So that's counterclockwise, but the low priority group, the hydrogen, points forward. So we take the opposite, which is S. And so in question 2 then, we're just kind of taking all of this to the next level. Provide a name for the following compound. So we'll start numbering this one over here. And so we have an 8 carbon chain for octane. And it's going to be 1 bromo, 1 cyclohexyl, 6 isopropyl, and then 4, 5, 7, 7 tetramethyl octane. And I didn't draw it in, but we're going to assume this methyl group points forward. So we're not quite done though. We still need to do the stereochemistry. And we have chiral centers at 1, 4, 5, and 6. So we need to go through and determine R and S at each one of those chiral centers. At carbon 1, the bromine is highest priority, followed by the cyclohexane ring and the carbon. So we have 1 R. At 4, the carbon over here is highest priority, second and third to the methyl. That's also R. Our next carbon, the methyl is third priority. The hydrogen pointing forward is fourth. Now the carbon on the right is bonded to 2 carbons. The carbon on the left is bonded to 2 carbons. So we have to go now 1 carbon further. The carbon on the right is just a CH2, whereas the carbons on the left are both bonded to multiple carbons. So higher priority here and second here. That's counterclockwise, but again we take the opposite because the low priority hydrogen is pointing forward. So that's 5R. And finally at carbon 6, we have to the left a carbon bonded to 3 carbons. That's higher priority than either of the other 2 bonded to 2 carbons. Second priority to the right, third down here is clockwise, but again take the opposite because the low priority group, the hydrogen, is pointing forward, is 6S. So as we continue to do and learn more nomenclature in this course, don't forget your stereochemistry. Those R and S terms are part of the name of a molecule. And if you don't include them, your name is not, for your molecule, is not complete. So the rest of the sheet is just these pairs of compounds that we're trying to identify as, and I'm just going to abbreviate, E for enantiomers, D for diastereomers, CI for constitutional isomers, and we'll use S for same. So this first compound, you can see we have two stereocenters located here and here. And between our two structures, we've inverted or reversed both stereocenters. And remember, when we invert all of the stereocenters, that's the definition of enantiomers. In part B, this one looks a lot like part A. It looks like we've inverted, our stereochemistry again. But are there any chiral centers here? So if you look at this carbon, for example, it's got two identical substituents. And so these are not chiral molecules, and therefore they're going to be the same. All right, what about in part C? So what I did in part C was I kind of rotated the entire molecule like this to get to the second structure. So let's do that and rotate it back and see what happens. And if I do that, you can see that, and this is a great case where models will help you. That stereocenter is the same. That one's the same. That one's the same. But this one has been flipped. Since we flipped one stereocenter, but not all of the stereocenters, those are diastereomers. Part D, we only have one chiral center. It's been reversed. That makes them enantiomers. Part E, you can see we've got some chiral centers, and we have reversed them. However, right down the middle of these molecules is that internal plane of symmetry we've talked about. And that internal symmetry is characteristic. It's what we find in a meso compound. Meso compounds are by definition achiral and means that they're the same. In F, we have two chiral centers. One's the same, one's been reversed. Those are diastereomers. G, just like in part E, we have that internal plane of symmetry. So these are, again, meso compounds and therefore the same. Part H, well, you can see we've literally taken an alcohol and moved it one carbon. So those are just constitutional isomers. In I, we've reversed one chiral center, but not the other chiral center. Those are diastereomers. Part J, these are just resonance structures of each other, and that means they're the same. K is another one where your models will help you. This one's, again, not as obvious. But all I did was I rotated about that bond. And so this is a great case where you can use your model kits, but it's also a great case where determining R and S can help you quite a bit. We have S here and R here, whereas in this one we have S here and R here as well. Since neither chiral center changed, they're the same. In part L, this carbon's not chiral. It has two of the exact same group, two methyl groups. So these molecules are both achiral. Therefore, they're the same. And that's it.